will be just a very brief survey over dynamic movement primitives. These ideas are derived from a particular phenomenon, which I don't think that analogy really works, but that's, if you read their papers, that's what people in this field refer to. And it's the notion that, it's always this notion that the brain is super complex, and to make a movement is very complex. And so the idea would be, maybe what you do is you just have a neural circuit that can do certain time courses for certain movements. And then to get different movements, you just superpose these primitives, these simple time courses. That's sort of the general notion. And so the concrete work people often refer to is this old work from the Beatsy lab at the MIT. And that's, it's a lot of subtle things about it. It's a frog. It's actually, in many cases, a spinal, so where the brain has been cut off, but it can also do that really with a intact frog. And the frog's leg is in a couple of different positions fixated there. And for instance, in one simple version, you're eliciting the wiping reflex. So these frogs have a reflex that if you stimulate the skin somewhere on their body, they will make a wiping movement sort of to get rid of the irritating stimulus there. That's what you're tapping into. And these reflexes are done by the spinal cord. As you can see these reflexes even if the brain is disconnected. So it's a spinal circuitry that does that. And they're tapping into that, in that what they are doing here is that they are electrically stimulating in the spinal cord. So you're really preparing the animal, and you can insert an electrode and you know where you're stimulating, and you're stimulating particular so-called premotor neurons. So they are not directly connected to the muscles, but to other neurons, or interneurons, as they say that. And when you're electrically stimulating these, the monkey wants to make, the frog wants to make a certain movement. But in this experiment, you're not actually allowing the animal to make a movement. And once it makes a movement, there's all kind of complex stuff happening, because then sensory signals from all the muscles will come back to the spinal cord. So Li Zhang will give you a little bit of an idea, not in frogs, but in general, about how these spinal reflexes work. So to not deal with that, they're just allowing fixating the limb, and they're measuring the force that the limb exerts. And what you find is that as you vary the position where the limb is on this grid, you measure the force that is elicited by the same stimulation, you get a vector field. This is a real picture of a vector field. That is, in this location, the limb makes this force, here it makes that force, so on. You see, it's a little random. And then they use all kinds of smoothing techniques, interpolation techniques, to get an estimate of the vector field in all other locations. And so, for instance, they would say this is a convergent vector field. Overall, it tends to have some equilibrium that the arrows point to in the middle. And so one of the findings of this literature is that you find only certain kinds of vector fields, convergent ones, parallel ones. This would be another convergent ones. They try to map that onto where in the spinal cord you're stimulating. Frankly, this looks so nice, but they are constructed from these very crude ones and then interpolated so that it looks so nice. It's really just because of the interpolation. Right? So one can discuss a little bit how valid that is, but they have some statistical technique where they say, are these convergent vector fields just by chance? And then they have some argument that it's more often than by chance, so there must be something special about convergence. And so from this, the notion arose that these vector fields could be some kind of primitives. That is, if you have this vector field and you start here, you would maybe converge here. If you start here, you would converge there, and so on. And in particular, you also find sometimes that you can really predict the vector field that when you stimulate at two locations at the same time. So, for instance, you have this vector field when you stimulate in one location, this when you stimulate in the other location, and then I don't remember which one exactly that is, but if you stimulate in both locations, you would get Oh yeah, this one is when you simulate both locations, you see it get an attractor here. And this is when you're just adding these two vector fields, so it would also get an attractor here. So it's an idea that these neural circuits in the spinal cord could be primitives, and by superposing them, you could now create a movement to some intermediate position. So that's sort of the story. Now, you will see that the dynamic movement primitives create vector fields like that. It's somewhat superficial analogy because these are really forces. The frog is never moving along these trajectories, right? Because the leg is fixed and the forces are measured statically from these different positions. And if you were to allow the limb to move, would it actually move along these vectors? It's a totally different question because of the reflexes that would change the forces that are experienced at some moment in time. So there's a certain gap between this idea and the following idea. I'm just telling you that's what is in these papers, and that gap is maybe problematic. The dynamic movement primitive approach, developed much later, is inspired by that, but you can just understand it technically. And so it has the idea of a timer inside. Now, this is not a limit cycle timer. It's just a damped harmonic oscillator. So this is a fancy way of writing a harmonic oscillator. So the variable here is some one-dimensional position of some planned end effector trajectory. You see here's the second derivative. Somewhere in here is a elastic term that is only proportional to the y, the position itself, with a negative sign. That would be like a spring, right? A stiffness kind of parameter. So if nothing else was here, then you would see that this is a spring with length g. So if nothing else, you would have zero acceleration if your length is at g, and g will then later be the target value. So that's where you will make the attractor. It's not yet an attractor because it needs damping to be an attractor, right? This will be an elastic system, would keep oscillating forever. But if you put in a damping term, that will be a velocity dependent with a minus sign, then it might come to this position and zero velocity. So if you have zero velocity and you have y equals g, then all of this is zero, and then you would have an equilibrium. It would be stable, as you could figure out from the negative sign here. So it's just a bit fancy way of writing down the harmonic oscillator. In fact, in the model, they typically write it as second order system. And we did that before, right? You can write a second order system always by introducing a variable for the derivative. So y dot is z. And then, it's a first order equation in y and z. And this is the trivial second equation. Z would usually be velocity, but they put this toy on the left, so it's not quite velocity. No, but it's just for statics. So that's the trick of how they make the timer have fulfill constraints. So by setting the fixed point to the right values, to final velocity 0 and final position or equivalent position g, you can set the goal point where this system will come to rest. The idea will be that you're planning, for instance, to intercept a ball and so on, like similar to the examples I showed, and the distance to the ball would define the amplitude of the movement system. And so you would insert that here, and as a result, your trajectory will really move all the way to that location. If you've never before experienced that location, it would move there because the space oscillator has that property of generating time forces that end up in that position. It might end up in a very damped way and so on. This is part of the design, but it will end up there. Now, there's another term here that's an external forcing function. So when you add this function, this will turn out to be time dependent. Excuse me. Then you will have a temporally forced and non-autonomous harmonic oscillator. You may know a harmonic oscillator that you drive, you can impose on it time trajectories, where the harmonic oscillator is essentially like a low-pass filter. The harmonic movement will, will lag behind the forcing function and will smooth it, and will smooth it with a characteristic frequency window that depends here on the stiffness and the damping. They're combined in some funny way. So alpha times beta would be the stiffness, and alpha alone is the damping. And it's written so that you can express critical damping when these two would have the same units and the same value if expressed in time units. So that's the base oscillator. That's how they do the timing. Now this forcing function is constructed in some special way. So what they now want to do with this forcing function, they want to impose more detailed time shapes that are not harmonic. So the notion is you want to do any movement, not just some harmonic movement, but you still want to make sure that you arrive at the target at the right time, or with actually not at the right time, with zero velocity. It will not be perfect at the same time. And so the forcing function is now built from some Gaussian terms. So this is a superposition of Gaussian terms. Now these are essentially Gaussian terms. These are weights. This is just for normalization. The Gaussian terms here, 20 terms plotted, they are centered around different positions. Now the funny thing is, we'll look in a moment, x actually turns out to be time. So these are functions of time. Here it's written as a function of time, but you will see in a moment there's a recoding of time. And so they are centered on different moments in time. It's really funny. I mean, that is a little typical robotic, man. This would be in the nervous system very difficult to realize right now. How do you have a clock and know where you're on time and read out these functions? So these are sort of time staggered scores. You have these functions available somehow in your computer, and you can activate them and mix them to create just any time shape. That's the idea. And the recoding for pure mathematical reasoning is that this is a timing dynamics that is, rather than measure everything in time, you measure everything in terms of x, which is governed by this equation. That's the equation you all know very well. That creates exponential relaxation, right? That's what's shown here. And it's organized such that it always starts at 1 initially, and then it decays to 0 in a time that's characterized by tau divided by alpha. And you can choose that time. You can also see the drawback of that rescaling, because you know, when are you close enough to 0, right? When does it actually end? Some cutoff that's done algorithmically. In the end, you have some criterion when you say, "Now I'm done." Now, time is a better variable because it really goes from 0 to 1. Now you could say, you know, is it 0.9999 or is it, you know, 0. Or is it 1.0001 or whatever is my final time, right? But here that becomes much more severe. Where in time does your x really reach 0? In fact, they reset this timing variable every time a new movement is done. So jump, algorithmic. Right? So horrible for us who are so neurally inspired, because it's very algorithmic. And that actually is a practical problem. But it has certain mathematical properties that they exploit. So what they can do is now, when they replace time by this funny variable, they have this forcing function. Now here's the trick, they can represent then, sort of turn on and off this modulation function. And see this in two ways. One is when x reaches 0 at the end of the movement, x will reach 0, the forcing function is 0. That means in the end, when you're done with your movement, you will have no forcing function. You will have the harmonic oscillator, and therefore your timing variable will have the attractor at y equals g, which is what you planned, and at y dot equals 0. Now that's how they make sure that this modulation of the time course is just a little game you play while you're moving, but it's off when you're done. And similarly, this term here scales this function with the amplitude of the movement. So this makes sure that, so g is the final time, you know, it's the initial time, that when you're covering a larger distance, you're scaling up these forcing functions so that they, you know, their modulatory influence is sufficient to really affect time. Imagine you have a very large amplitude. That means that in the original system, these terms are very large. If this doesn't scale with that, then the modulation is less important. So by scaling it with that same factor, you're making sure that you, for different movement amplitudes, you always have the same modulatory component on that. So, so one can fit that. I'll show you how the fitting goes, so that movements follow a desired trajectory and also arrive at the target. So here's an example. This is a variable y, the variable single variable that is supposed to go from 0 to 1. And the dotted line, it's very small. You see a little dotted line, and here you see a dotted line. That is a target, that what you want to fit. Here it's a polynomial, I think, like a fifth order polynomial. And so what you want to do is you want to arrive at the position, the 1, smoothly. So the velocity is 0, even the acceleration has to be smooth, at time 1. So that's when you want to be there. And you still want to do it in the style that that target gives you. So in the detailed time course should approximate that. You see here, approximates it relatively well. It's a little undershooting here, a bit over undershooting there, but overall it's pretty good. That's all. That's really the goal. And the mathematical framework just makes it that fitting, which they call learning, works well. This is an example with 20 such kernels, so plenty of parameters to do that. This is the same example. So this just explains that. I don't have to go through that again. I think I will perhaps come back to that. First, I want to illustrate how that actually works intuitively, and then I want to show you how you learn that. Now let's first look how you actually learn these weights. So you see, there's no magic. So what you need to do is you want to determine these weights. That's the only thing that you can fit, right? These weights of how you modulate the vector field. These weights W, so that the trajectory that you generate out of the system matches some target trajectory. So here the target trajectory is called demo. So for instance, would be the idea that a human hits a tennis ball. You record these movements. Actually, Auke Eisbert, who's one of the authors of this, really did that in Canada, in Japan, I think, with humans who hit a ball with a racket, and you record the racket motion. And now you want the robot to learn to hit the racket like the human. So in the sense of making these kind of trajectories as the human does, but it still achieves collision with a ball. So it's, even if you now let the robot hit a ball that the human never hit at a particular distance, it will still arrive at that distance of that ball in the style of the human. That's the notion. So that's the movement style. The details of the time course is done by F. And this makes the generalization that you can hit new locations. It will only work within a certain range. If you move too far, it won't do that. So in these cases, these Y trajectories are from the human data that you fitted. In the example I just showed you, the dotted line, it's the polynomial that you feed to that system. So the idea is that you take the trajectory and you write, essentially, you know what kind of force you need to generate by inserting the trajectory into this equation. And you say the target force I need is the kind of force that I would need to make the target trajectory a solution of this equation. And so on the right-hand side, you're just injecting here the observed time course, and you're computing this. And then you can know that if you're inserting this into this equation, the demo trajectory will emerge from this, right? Ensuring that it's the solution. And so so now you have this target force, and now all you have to do is fit these W's so that this function approximates that target force. So literally that just means that you have to minimize the square error. So the target force minus these funny terms here. This is just put into one term. The psi is putting all of this in one term. These things here squared have to be 0. The psi term is in here. The normalization doesn't play a role for the minimization, right? You can drop that. So this is one possible cost function that you can minimize. And it turns out that that can be analytically solved. Essentially take a derivative with respect to y. You have to square 2 times this. You can figure that out. So you can actually analytically derive an equation from the W. That's what makes this so attractive and very, very simple. So if you figure that out, the gamma matrix just takes these psi functions at particular points in time, and this is just the different target function at different points in time. This is this prefactor at different points in time, and if you combine all these together, you get this, get the weights. Now that's how that's done. And so that's what they did to achieve a fit here. Oh, see that it's not for what it's worth. Good. Now you can also do periodic movement with that. The periodic movement would consist of just using transforming this to phase. So you don't use this, also you use a phase with a constant amplitude, and then you modulate the amplitude with this kind of thing. So it's much simpler to do that in periodic. I'll skip over that, the same kind of idea. And this just illustrates how you can scale these primitives. So when you scale the parameters in those, you can span a whole family. By changing the sign, you can flip it this way for the velocity. Don't remember, actually, there's two different parameters that are scaled here. I don't remember which one are those. This is scaling of time. So in the primitives approach, there's always the idea that you would do that. There's just one system like that, one timer. So you would have a timer for one task. All of this is always just one task. But you could drive different degrees of freedom from that. So for instance, we just looked at the case now where one position to control, but if you want to control the positions of the whole racket, you would have a couple of position, velocity, acceleration variables, and they would all be driven by the canonical system, the base oscillator, and you'd have to know how it maps onto these individual movements. And here's an example. This is actually a case where there are two variables. The first variable is supposed to do this thing. The second variable is supposed to do that thing. This would be the two-dimensional phase diagram. So one variable and the other variable. And so now you see how they relate to this frog vector field, because if you now look at the resultant dynamics, so this is the little vectors are y1 dot as a first component, y2 dot. So this is the vector field of the dynamics, right, of y. Now these two base oscillators for the two dimensions, driven by the same underlying timer, phase variable x. And then you see that there's always an attractor. Like there's always a convergent point, and you can sort of intuitively see that as you move in time, the convergent point moves first along y1. It first moves to the left, I guess, right here. Initially, it's here. Then it's moved a little further left here. The convergence point is here, and then ultimately moves to the right. As this goes to larger values, then the convergence point moves somewhere to the right. And along the other axis, I guess, must be just moving up, right? Initially, it's here, and then it moves. It's a little higher, and then it's higher. So the convergence point sort of tracks these trajectories. Now, it's not entirely true, because you see, for instance, here the attractor has moved further to the right than where it ends up being. So what actually happens is that the attractor overshot here and then returned. And that is done by these forcing functions. So what the forcing functions do is that they move around the vector, they add to the vector field, they move around the vector field so that going to the attractor, the system does the right trajectories. So here the initial, the system is initially here. And this is always, how it would move to the attractor, right? Is that right? No, it's not right. It's sitting initially here. And then the attractor moves away, it tracks here. The attractor would be somewhere here. It tracks it with delay. And you see here, for instance, the attractor is here. So this drives the system in this direction. And then the attractor moves toward the system. And so it stops here. Now this makes the break, and that's how it achieves that. So that's the analogy to that vector field. Now, This is a purely mathematical vector field, but this is a purely kinematic approach. It's just a planning variable x and y, y1 and y2. And with that trajectory, you're making sure that you arrive with zero velocity at the target, and in between you can deform it to shape the trajectory. While in the frog case, this was actually physical force that the muscles generate. And when it was isometric, because the muscles were fixed. So when the limb moves, all kinds of things happen. That would be physical dynamics. That would be control. That's what I'll discuss next week. And clearly, this doesn't actually address that. It's just a metaphor, I would say, metaphorical analogy. Okay. Last thing I want to mention about that is that they did include obstacle avoidance as some feature. It turns out, however, if you look into that, and they cite that correctly, that it's really just the attractor dynamics approach that they insert there. We generalized the attractor dynamics approach some years ago into arms, into vectors. And the idea is that when you want to avoid an obstacle with the end effector, you're moving to a target, want to avoid an obstacle, what you have to do is add a contribution for a desired velocity that steers you away from the obstacle, a certain angle away from the obstacle. And that's something that one can compute. So you compute some direction. Essentially look at the vector that points to the obstacle versus your current velocity, and your this is the distance vector, I think, between the distance to the target and the distance and the obstacle. And then erect this, if you find out this angle here, and then you add a vector to the velocity field that points in the appropriate direction. You add that term to the equation, then it does obstacle avoidance. And for instance, here's an example of the system doing that, making trajectories around that. So we had proposed that same kind of idea, not using the other part, the harmonic oscillator we use instead, Hopf oscillators. It turns out, that's the irony of that humans actually don't avoid obstacles like that. And we have a whole project where we did that, and where actually one of my students is still working on mathematical refinement of, this was experimental work in human movement. I decided not to go through that in detail because it uses kinematic irregularities that only Lei will present. But you can perhaps intuit why we wouldn't do that. For instance, when you have an obstacle like that as a human, you would never go around it in this funny way. You always would go over the obstacle, right? Maybe you would incline the plane of your movement, like go over, and maybe you go on the side. You never would go below, because things don't float in space. They usually are attached to the table, so they stand up from a table surface. And so you have what we call lift and transport. That is, you have a dimension. It turns out that what humans do is that they have a lift component. They always make a movement that elevates from the initial position to a peak, and then returns to a lower level when you grasp things. And obstacle avoidance consists of manipulating the height of that lift, and of manipulating the timing of what we call the transport. So as you move to the target, essentially when it's an obstacle, you're slowing down your transport to allow the lift to get high enough. And then when you're past the obstacle, you're just resuming your usual speed. So you're modulating the timing of the movement to make the obstacle avoidance. So it's quite different from this idea, which we also published. So we also made the same mistake. But for roboticism, you can do that in some way. It's not very consequential, that kind of idea. So that's all I really want to say about that. They had some ideas about coordination, that is, these abstract time variables could be used to insert stuff there, but frankly, nothing really interesting happened there. So I'm not very convinced by that. Now, this is an influential approach, however, and it's influential because it is this idea that learning time courses, a very general thing, a difficult thing in general, how to learn time courses. And so here, this has been successful in learning time courses, and it does it essentially by having this phase oscillator. So you give a time course already, and then you just modulate. And that idea is being used in different kind of robotic settings. There's an alternative to that that's called reservoir computing, where you have a lot of neurons thrown together with some random connections, and they tend to oscillate or to generate complex time courses, recurrent connections, make the time courses, and then you just learn to extract from them those time courses whatever you want to extract, like learn in supervised fashion. And that's not entirely different, because rather than having a harmonic oscillator, you have this more complex set of possible oscillators from which you can take what you need. And what we're doing is that we're, in my lab, we're actually doing something in between. We're assuming that there are batteries of oscillators with different parameters, and that you're combining these batteries. So it's not as random and uncontrolled as a reservoir, but it is still a whole ensemble of oscillators from which you build. You could call those primitives, but it's actually continuously many primitives. So it's not the same notion of having just discrete different primitives. Yeah, and the other thing that it does, so that makes it attractive, this learning angle. It's purely kinematic, so it doesn't address control. We'll get to that next week, even though we'll just review the conventional stuff about that. And the way it addresses coordination is somewhat similar, limited. Interesting about dynamic movement primitives would be to have it for different tasks. There are other people who have developed this in many different contexts, but typically it's a set of dynamic movement primitives for every task, and how to combine them, and how to, for instance, activate one task versus another, as I was showing in the robotic example in the previous lecture, right? Where you would have to update and then switch and so on. That is current work. There is some work on that. It doesn't really quite fit into this learning paradigm. So it's a little different direction. That's something that we're also very interested in. That runs under the label of behavioral organization. Okay, so I close this little excursion into dynamic movement primitives.